Okay, so in this example we have actually a 3D object undergoing plane motion, so we can go ahead and extend the results we've been using for two-dimensional systems to 3. And in particular we're told that this angled bar specimen is rotating about a vertical shaft at point O with a given angular velocity and angular acceleration, with directions indicated in the figure below. And given this information, we're asked to determine the velocity and acceleration of point P on the end of this bent bar specimen. So to do this, we're going to try to relate the kinematics in a rigid body sense from essentially using 2 points. A point where we have a lot of information, in this case point 0, the fixed point, or point O, the fixed point, and we'll try to extrapolate from that to what's going on at point P. So to do this, I'm going to take advantage of the axes that are already laid down in the problem, and I can first of all sketch out unit vectors. So of course I'll use here my conventional I, J, and k unit vectors, and if I do that, then it becomes a relatively straightforward application of the equations we've already been using in this chapter. So in particular, what I can say is that the velocity of point P is going to equal the velocity of point O plus the angular velocity of the rigid body crossed with the position vector of P with respect to O. If I make some substitutions here, we know the velocity of point O, because the fixed point will be 0, in this case a vector 0, because it will be 0 in all 3 directions. I'll add to that omega, which will be a scalar quantity in the k direction, and I'll cross that with, in this case, the position vector that describes the position of P with respect to O. In this case, that's going to be some distance 0.5 meters in the I, plus 0.25 meters in the J, plus in this case 0.05 meters in the K. And now I simply need to do this cross product. So if I do that, I'll have K cross I, and in this case you can go ahead and leave omega as a variable or plug in the number, but K cross I is going to give me J, so I'll have 0.5 times omega in the J. K cross J is going to give me minus I, so I'll have minus 0.25 omega in the I, and K cross K is going to be 0. So indeed this will be the velocity associated with point P. Now I can reproduce this with acceleration to get the answer for the acceleration of point P. So in this regard, I can say the acceleration of point P is going to equal the acceleration of point O plus the angular acceleration of the rigid body across the position vector r of P with respect to O. And then because this is a 3D problem, I'll choose to make this plus omega cross quantity r of P with respect to O. If I go ahead and do the substitution here, the acceleration of point O will be 0. The acceleration of alpha will be, in this case, likely a negative number because a clockwise angular acceleration in the k, so that alpha scalar would be a negative number. And I'll cross that with the position vector, which in this case again is 0.5 meters in the I, plus 0.25 meters in the j, plus 0.05 meters in the k. And I'm going to add to that, again, omega in the k, cross with the product omega in the k, cross with the position vector, which again is 0.5 in the I, plus 0.25 in the j, plus 0.05 in the k. Sorry to run over the figure there. So again, computing this acceleration is basically an exercise of taking cross products, and so we'll go ahead and do this, trying to be systematic. So if we start with the first term here, the angular acceleration across the position vector, I have k cross I, which gives me a j term, so I'll have 0.5 alpha in the j. K cross J gives me a negative I term, so I'll have minus 0.25 alpha in the I, and K cross K will be 0. I'll add to that an omega in the K, cross with the product resulting from this term inside the parentheses. So K cross I will give me a J, so I'll have 0.5 omega in the J, and K cross J will give me minus I, so I'll have minus 0.25 omega in the I. I can finally do this last cross product here to wrap up my answer. So if I do that, I'll bring down the 0.5 alpha in the j, minus the 0.25 alpha in the I, and then I'll have k cross j is a minus I, so I'll have minus 0.5 omega squared in the I, and then k cross I is going to give me a j, so I'll have minus 0.25 omega squared in the j. I can now just simply group like terms, and if I do that here, what I'm going to have is quantity minus 0.25 alpha minus 0.5 omega squared, and all of that will be in the I, and I'll add to that a 0.5 alpha minus 0.25 omega squared, and all of that will be in the j. And that will give me my final 2 answers for this problem, namely the velocity of point P, which I've highlighted here in yellow, and the acceleration of point P, which again I've highlighted here in yellow. From this point forward, all you need to do is plug in the numerical values for omega and alpha, making sure that you take care of the signs involved here, keeping in mind that clockwise will be negative and counterclockwise will be positive. With that, I think it about wraps us up. Best of luck as you work through this problem.